So the talk I'm going to give is about Talbot effect, Gauss sums, and superoscillation, three topics from three different areas: Talbot effect, classical optics, Gauss sums come from number theory, and superoscillations. And I'm glad that Yakir kind of introduced them as one of the many interesting and surprising consequences of this reformulation of quantum mechanics, and in particular of weak measurements. So the talk is going to show how some of these objects come together, and we'll display one of the effects or applications, if you want, of superoscillations. This is a joint work with Fabrizio Colombo, Irene Sabadini, and Alain Iget. Fabrizio and Irene are here with us today, and they're going to give additional talks later on. So I will only skim the surface of superoscillation because, in fact, Fabrizio will speak just after me, and this is kind of almost an introduction to some of the things he will say. Both Fabrizio and Irene are from the Politecnico of Milano, but they're very frequent visitors here and long-term collaborators with Yakir. Alain Iget is from University of Bordeaux, a Fourier analyst. And he got interested in these matters by reading something that we wrote together with Yakir, a memoir of the American Mathematical Society, The Mathematics of Superoscillations. And so he became then also a frequent visitor here. So every November, December, Iget is here to work on these matters. And that's actually something that I didn't mention before, and I wanted to, about Yakir's impact. Not only we spoke about the impact, obviously, on physics and then on the university, but also how many people from different fields have become attracted to the mathematics that originate from some of his ideas. And so that's why we now have a fairly significant group of people that really never thought about superoscillations before and are working on them now. So let me see if this, let's see, this is supposed to work? Maybe I'll press here this button. This is good. I don't want to make this more complicated than it needs to be. So this is kind of the sketch of the presentation. I will remind us all about the Talbot carpet, though you probably know it better than me. I will remind all of us about what Gauss sums are. Very basic introductions to superoscillations, again, referring you to some of the other talks where this will be discussed in more detail. A kind of a generalization of the idea of superoscillation, what we call supershift. I'll discuss a little bit what we mean by that and why that's relevant to our discussion. The modelization of the Talbot carpet through the use of the Dirac comb, and then finally to bring them together, how the superoscillation allows us to calculate the Gauss sum to provide an asymptotic approximation of the Gauss sums. So this said, let me start with the Talbot carpet. This is a frontispiece of an old book from 1665, written by an Italian Jesuit priest, Francesco Maria Grimaldi. This appeared actually a year after his passing. That's why it's a posthumous work. And as you see from the title, is the Math and Physics of Light. And most texts that I've seen refer to him as the first person that actually talk about diffraction, which is the topic of the Talbot carpet. And it's interesting because, of course, it's kind of early in the development of the theory of light. And I have a picture here of what is called proposition 1. And I'll read the title of the proposition. It says, lumen propagatur seu diffunditur non solum directe refracte reflexe, sed etiam alio da un quarto modo diffracte. So it says that the light propagates or diffuses not only directly by refraction and by reflection, but also in a fourth way, diffraction. I confess that I didn't read what the guy actually does about it, but it's the first time apparently that this word appears, and so people refer to him as the person who opened the discussion on this topic. The example that I wanted to refer to, that this, of course, is a modern image. This is taken from Wikipedia, by the way, of the Talbot carpet. which is the kind of the image that describes the Talbot effect, that was first described by a guy called Talbot, for good reason, in 1836. So we're going to come back to this later with some more detail about what's happening there and how you can calculate where these dots appear. But let me just tell you what we are looking at. So you can imagine to have a screen with regular holes at regular intervals. And then you have a light, a monochromatic light that hits the screen, and then it propagates across the holes. And so what you see is you see this interference phenomenon. So you have a bunch of light and darkness. And there are two basic parameters in this picture. One is the wavelength of the incoming light, and the other is the distance between the holes. In this particular case, they're assumed to be equidistant. So on the base of these, you have different images that are created, but the thing that we want to notice about this particular picture is that after a certain distance, that's called the Rayleigh distance, the Talbot distance, you get exactly the same image that you started with. So if you look at the very end of the picture, it's exactly the same light that you started with. And then if you go, say, halfway, you see the same thing, but with a shift. And then if you look at the different fractions of the distance, you have different phenomena in which you either have the same location, but with a diminished distance, or the same location, diminished distance, but shifted. So that's an interesting phenomenon, and it's been very well studied, so there is nothing really new that one can say about this. So what this is a diffraction caused by the waves that are incident to this grating, and they pass over, and then they interfere with each other. There is what I call the Talbot length. I said before, it depends on these two quantities. Lord Rayleigh showed that the Talbot length, in other words, the distance at which the image replicates the initial image, can be given by lambda divided by 1 minus the square root of 1 minus lambda square a square. Now, if lambda is much smaller than a, remember a is the distance between the fixture, the holes, then lambda square over a square is very small, and so the square root of 1 minus lambda square over a square can be approximated with the first order Taylor by 1 minus lambda square over 2a square. So the 1 minus 1 cancels, so you're left with lambda over lambda square over 2a square, and that gives you 2a square over lambda. So that's a decent approximation for the Talbot length that we saw in the previous picture. So if I go back quickly, that what you see here, the distance between the base and the top of the rectangle, that's what the Talbot length is, and that's a 2a over lambda, 2a square over lambda. So what you see is what I described before. And again, we're going to come back later with a little bit more refined look at this picture. So I'll replicate the picture later in the PowerPoint. But at half length, what you see is the same image, but shifted. Quarter length is the same image with both the shift and half period, and so on and so forth. These are just, here for some reason I only looked at the negative power of 2, but you can look, for example, if you take a third of the length, then you don't have a shift. And so we're going to see specifically why that's the case very briefly. So that's one of the three objects of the talk. The standard mathematical modelization uses the Fresnel diffraction principle to model these, and reference for this is Introduction to Fourier Optics by Goodman, but you can find this described in many, many different places. Okay, so that's really all I wanted to say as introduction to what the Talbot carpet is, or the Talbot effect. And now I'm going to get to the second topic, so that, like they used to say in Monty Python, for something completely different, we go to Gauss sums. So the Gauss sums, the quadratic Gauss sums are defined by this sum of roots of unity. And they were introduced by Gauss, that's what I call Gauss sums, in maybe one of his most important, I mean, it's kind of hard to decide which one is the most important contribution of Gauss, but in the Disquisizioni Aritmetiche, 1801. In 1801, he proves the quadratic reciprocity law. Quadratic reciprocity law is maybe the fundamental theorem in number theory. The question you're asking, you have two prime numbers, you're asking whether Q is a square mod P, and that's one question, or then but you could ask whether P is a square mod Q. And the answer to these two questions is connected by the quadratic reciprocity law. So it's a very important result that actually is applied to many cases, and there are now something like 100 different proofs of that result. But one of the proofs that Gauss gives in discrete arithmeticas uses this Gauss sum. So that's why they are an important element in number theory. So this is the sum of e to the 2 pi I, a L squared over C with L from Z to C minus 1. There is a generalization of this, which is the one that is of interest to us, and they're called the generalized quadratic Gauss sums, in which in addition to the quadratic element AL squared, there is a linear one, BL. So you have the sum from 0 to C minus 1 of e to 2 pi I, AL squared plus BL over C. And clearly, if B is 0, you get the old quadratic sums that I described before. And the major reference here, or one of the references, is Gauss and Jacobi sum by Byrne, Evans, and Williams. Again, they play an important role in a bunch of different results in number theory. And so that's a kind of a different direction, if you want, a different ingredient for the talk, which on the other hand has stimulated the interest of another one of our colleagues here at Chapman that is becoming fascinated with superoscillations and from a mathematical point of view, and that's partly one of the reasons why that is the case. So now let me get to ingredient number 3 of the talk, which is superoscillating functions. So the definition up there, I think, is the one contained in one of the earliest papers of Yakir. It says superoscillating functions are band-limited functions which can oscillate faster than the highest frequency that they contain. A statement that almost seems paradoxical, but of course is not, and we see why and in which way this is the case. Partly is the fact that we talk about functions, but maybe the most proper thing would be to talk about superoscillating sequences. I'm glad that Yakir mentioned it before, because this came about in the context of weak measurements. I suspect the paper here that we have in 1988 is probably the first published paper, but maybe not the first place where it appears. I see that Jeff is nodding at the opposite of nodding. What is the opposite of nodding?
It's actually in a paper by Sanjay and Daniele brother. It's a preprint.
Oh, that's a famous preprint. Yeah, that's why I said published.
Oh.
Because yes, there is an existing preprint in which this is also discussed. And Sir Michael Berry has kind of done some very important work that, I wouldn't say resurrected, but brought them back to interest in Fassel and Fourier, a volume that, interestingly enough, was published to celebrate Yakir's 60th birthday. So there is a long history of celebrating Yakir's birthday with important discoveries. And so what are the superoscillations? You can mention how they emerge from weak measurements. So I'm going to give you what is the prototypical example of a superoscillating function. Another thing that is typical of, I think, of most of Yakir's work is how very simple things end up being very rich. So what do we have here? Here we have a function that depends on, if it's a function of the variable x. X is a real variable. And a is a parameter, also a real parameter, that we assume to be bigger than 1. And n, of course, an integer. And that's a very simple function. It's the cosine of x over n plus ia sine of x over n, all of this power n. It's hard to imagine a simpler function. So you can rewrite this function by using the Euler's representation of sine and cosine. So the cosine of theta is e to the I theta plus e to the minus I theta over 2. And the sine of theta is the e to the I theta minus e to the minus I theta over 2i. The I is important. So when you replace there the cosine, you get some e to the ix over n. You get some e to the minus ix over n. And then when you have the sine, you have the 2i in the denominator. So that cancels the I. So the I goes away. And so then you can collect the e to the ix over n, e to the minus ix over n. You take the power n by using the binomial formula of Newton, and what you get is a new rewriting of that expression in this way. So what do we see here? So it's a finite sum because it's the nth power of a binomial, and you have an exponent which is the collection of those e to the I x over n, e to the minus I x over n. So that's where the I ended up. And you have some coefficients, which are the binomial coefficients, and then, of course, there is this a that was in the expression before. So the coefficient is oscillating, as you see, it's a minus 1 to the j over to the n, and because a is bigger than 1, this actually explodes very quickly. And what you notice here is that all the frequencies of the exponents are 1 minus 2j over n, so they are all between minus 1 and 1. Let me go back for a second. There is another, so we rewrote this in Fourier terms. There is another way to rewrite this by letting n become large, then the cosine of x over n is 1 minus x squared over n squared. The sine is x over n. So you can throw away the second order term. So this expression, when for n large, becomes 1 plus ia x over n, all power n. And so as a result, you can show that the limit of this is e to the I ax. And so that explains why Yakir and called them super oscillating, because now you have the frequencies are bounded between minus 1 and 1, but the limit is an exponential e to the IAX with arbitrarily large a. And so, as the original definition said, these are band-limited functions, because 1 minus 2j over n is between minus 1 and 1, that oscillate faster than their fastest frequency, because you have e to the IAX with a bigger than 1. And now, the reason why this is possible is, again, because we are looking at the limit as n grows, and let me go back for one slide very briefly. This wouldn't be true if the coefficients Cj were not depending on n themselves. You couldn't have the limit of functions which are band limited between minus 1 would give you and 1 would give you arbitrarily large frequencies. But what happens here is that you are allowed to variate, to change these coefficients as n grows, and it's hidden in this coefficient is the ability to create this super oscillation. This is something that super oscillation have been studied now for many, many years. And one of the references I'm going to give at the end is what it's called a roadmap on super oscillation that was edited by Michael Berry that contains kind of the state of the art on super oscillation up to, I think, 2 years ago. So that's a very good reference. And they've been studied in a lot of areas, both from an applied point of view, from the point of view of what they say about the mathematics. And one of the big questions, and I know that Fabrizio is going to, his talk is really centered about the general theory that answers this question, is what happens if you evolve, according to the Schrödinger equation, one of these super oscillating functions. And I often joke with Yakir that whenever he asks me something, I need to hear it 5 or 6 times before I understand exactly what we are supposed to do. This is a perfect example, because the first time that Yakir mentioned to me the super oscillation was, I think, Shmuel was with us, and Jeff was with us, and maybe somebody else in the backyard of my home. I can't remember who the other person was, but I remember.
Roddy Kashir.
Ah, okay. I remember we had an easel, and Yakir gave a version of the, why super oscillation matter, and what we needed to be able to address, which was this question. But as I said, it took me a long, long time before understanding really what the question was and then working on it. So the question is, you take the Schrödinger equation, you take as initial value fn of xa, and the question is, do you still have super oscillation once you evolve it? And Colombo will show how this problem can be attacked. There is a general theory that we have developed on studying this, very large number of positive results, and they actually allows us to look at something more complex, more interesting, which is supershift, of which I will say a couple of words. And the interesting thing, and I'll mention this again as we get to the end of the talk today, The interesting thing is it turns out that the way, at least the best way so far to study this is a theory of convolution and infinite order differential operator in spaces of entire functions. So there is some analyticity hidden here that really becomes central. And I was talking with Sandhu a few minutes ago about that's really the core of this entire theory, is that these functions are real analytic, the one that we just described now, but they're a special kind of real analytic function. That's why we can deal with them in a special way. Okay, so I mentioned before that this is a special case of something else called supershift. So what happened in a superoscillation? In a superoscillation, you show that you can use the value of the exponential in a bunch of points near the origin, 1 minus 2j over n, to calculate the value of the exponential very far away. But in general, this could be, you could have a family of functions which have parameters that index them, just like if you think of the exponential e to the I lambda x, you can think of that as a family of functions, the exponential indexed by the parameter lambda. And it could be the case that you are able to take, to limit the choice of parameters and yet being able to construct every other function in this family as a limit for arbitrarily large parameters. So if you read this, I hate that these things when you try to write them precisely become unreadable, but that's the idea. You have a family of functions that depend on a parameter. You want to see if you can find a smaller family in which you limit the parameter to some interval and then still being able to generate all the other functions in the family. When this happens, we call this supershift. I'm going to give you an example so that hopefully will clarify better what I mean. Clearly, what we said before, the superoscillations are a good example of supershift. But if we look at the case, for example, the quantum harmonic oscillator, the T kind of ended outside, I don't know why. So let's say you take the quantum harmonic oscillator, so you have V equal x squared, and you evolve Fn of xa. That is something we wrote back in 2014, Journal of Mathematical Physics. This is the expression that you get for your extension. And so when you take the limit, now you get a function in which you don't have necessarily a superoscillative phenomena, but you have a supershift phenomena. Because you see, look at the exponents here where the a square appear. This is what this is what it comes out from here, and this IAX cos t comes from here. So now you have a family of functions. The family of functions are indexed by this parameter here. This could be a parameter lambda. And we can show that you can get arbitrarily large value of the parameter, in this case, A, by using only a small number, a limited, bounded limit of parameters within -1 and 1. So this is not, technically speaking, a superoscillation. You don't have that the exponentials appears, but as a superoscillating, but you have a very typical example of supershift. And the other thing that is important to point out is that in many cases, you have to get out of the realm of your nice functions and you enter in the case of distributions, or as I said before, I think here I mentioned even hyperfunctions. So solving the equation introduces singularities that then we have to look at something a little bit more complicated. So let me now get to how we model the Talbot carpet and how we can see how this superoscillation can play a role. So we start with the Dirac comb. Dirac comb is simply the set of openings that in your grid, equally spaced, which by Poisson formula can be written in the same way as a sum of exponentials. And now we can evolve the Dirac comb. So what we do is we take this as an initial value for the free particle, and we see what the evolution of this gives. And I didn't do, I think that Fabrizio will show exactly actually how this result is obtained. So in one of his first slides, that's probably the simplest possible case in when you take the case of the free particle, so V is equal to 0. That's maybe, again, the paradigmatic way by which we approach superoscillations, and this is what you would obtain. Again, if, because this is an infinite series of deltas, this, of course, is an evolution in the space of distribution. I don't know if the symbol is familiar, but D is a C-infinity function with compact support, and so D prime is the dual of the space, and those are distributions in T being positive, X being just a real number, and their opposite complex value. Well, one can show, and now this is a kind of lengthy but not particularly sophisticated calculation. It can show that you can take now this distribution, phi m, and you can restrict it to a given value of t. You can say, why do you write these rather than simply writing phi m of that value? But that's because it's a distribution, so you can't really talk about the value in the point, but you can talk about the restriction, and you still get a distribution. So if you take these, forget about the 2 pi over m squared. In fact, we'll remove them later on because you can normalize. These are the rational values. So remember what we were looking at before we were looking at the Talbot carpet. You want to look at what happened at rational values for t, and by doing some clever manipulation, you can show, by the way, that's not my work, this was done before, you can show that this is how you can rewrite the distribution. So if you want, you can, to simplify, this simply means that you're calculating that point, so that's what you have. So you still have an infinite sum of deltas, and the coefficients are the Gauss, generalized Gauss sums. And so what we can say is that you can use the Talbot carpet to recover the values of those Gauss sums, we say optically, in other words, by looking at it. So to do that, I need to do one more little manipulation of the phi. So I showed before how the phi is the evolution of the Dirac comb. So it's this infinite series. Then you can cleverly move with them, and you rewrite it as an infinite series of these deltas. And in fact, I can even simplify even more. And here I'm using this improper notation, but you know what I mean. It's the value of the evolution at the level p over q, just to make notation a little simpler. Is an infinite series of deltas in these points. So this is a delta in the x axis. Multiplied by this g prime is a variation of the Gauss sums, and you can go easily back and forth between the two of them. So now I want to show what does this really mean in terms of the carpet. So I repeat here the carpet. And so what did we see in the previous slide? We see that phi, which is, so this is t, and this is x. So phi of t means when you fix the value of t, you're fixing a slice in this picture. And what is it? At every value, at every p over q, you have a delta of this kind. So what can the delta says? Well, first of all, you can see that there is a difference when p is even or p is odd. Right? So if p is even, this disappears. You don't have that. So you have the delta at the point x minus k over q. So what you have is that at all the point where you have a replication, so to speak, of your deltas. And oh, that's a very good question. The intensity is due to the fact that actually there is this factor here, 1 over q, and then you have to calculate what those values are. But that's absolutely. So that's how you get it. And we are able to calculate those values. So there is a well-defined theory of that, and that gives exactly, thank you. And so that's what you obtain. You obtain these deltas, which are in, the distance, as you see, decreases with 1 over q. So if you take 1/3, which would be somewhere here, right? That's 1/3. Yeah, you can see that's 2, this is 1, and this is 1/3. Then you get smaller distance between the two objects. And the shift, it's only when P is odd. So you have now a nice picture that really tells you, describes exactly what is happening to your Talbot carpet. Now, how do we bring in the superoscillation? Well, let me go back for a second, and then this should, when I'm here, what I see is that this is a series of exponentials with arbitrary large frequencies. And so I can imagine that I should be able to use the fundamental principle, if you want, of your super oscillation, the key point, which is that you can approximate these arbitrarily large exponentials with band-limited exponentials. So that's one of the things that we have used also in a variety of other situations, and allows you to, you can show that the approximation is good enough, and that you can really truncate, so to speak, the K, the number of holes you're looking at, and get decent approximation for the values that you're looking at. So to begin with, what we do is we regularize the Dirac comb, so we do convolution with the C2 function of compact support. In fact, we're going to take this psi to be supported between -1 and 1. You study the evolution, and this is really nothing but the convolution of already the evolution of Dirac comb with the infinity, with the compactly supported function, the regularizing function. And this is the result I'd written before. And now you can use the fact, let's say you take support of psi between -1 and 1 and psi of 0 equal 1. And then what you have is that the intersection of the support of phi m and the shifted pi is actually really only one point in which the value is 1. So that's how you, by taking the duality bracket of your phi m, which is here on the top, with the shifted of psi, what you get is simply the value in 1 point, which is g of minus p jq. So now we have a precise expression for the g, for the Gaussian sums, by using the duality bracket of a C2 function. The reason for C2 is because you need some regularity, and 2 is enough in the calculation. So, but you can imagine of this being a C-infinity function compactly supported, peaking in 0 equal 1. And that's how you reconstruct completely. But then, and that's where one can say, well, very nice, but this, I can actually approximate this phi m. That's where I can use my super oscillating properties. And so I think the next result is not very nice to look at, but I'm going to show in the next slide with these constants here. But what you can do is you can actually approximate your G by taking the values in a finite number of points of psi hat. So this gives you a way by which you can, the previous slide shows a accurate calculation of the G, of the Gauss sums, which is the translation, if you want, of what we saw in the picture. So you have an optical image, then you have a precise calculation, and now here you get an asymptotic calculation, which uses the fact that you have super oscillating behavior. The coefficients are the one that one would expect. So this is a kind of an unpleasant proof, but there is not surprises in how it works. And so this allows you to reconstruct, if you want, the Gaussian sums in a asymptotic way. Now, one question that one could ask is, what if we had different potentials? So all of this that we have done, and now we are abandoning the Talbot carpet, but all of this theory was developed in the case that v is equal to 0, and these are the results that we obtained there. But one could try to apply similar process to other v's, and Fabrizio will show a wide variety of this. But in particular, for the case of a periodic, smooth periodic potential of that form, then you can actually calculate explicitly the evolution, and we can demonstrate that even there you have a phenomenon of supershift. So that's a more complex result, because the presence of V makes things more complicated. And as I said, Fabrizio will probably talk a little bit more about that. Let me close by discussing very briefly a couple of other developments that I think are interesting. And I was talking with Sandu before, and even though we are still in the refining process here, but one of the questions that arises, so there are two things that have to do with analyticity here. The first is a remark that Yakir made early in our approach to these functions. What does it mean to be super oscillating? It means that you know infinitely many values near the origin, and this allows you to calculate the values anywhere. What does it mean to be analytic? It means that you know infinitely many values in the origin, so you have only one point, but now you have all the derivatives, and you can calculate the function everywhere. So there is an obvious relationship between two. In a way, being super oscillating is maybe a form of weak analyticity to some extent, but there is a similar flavor. The second thing that emerged that was interesting is how do we do all of these results? So here in the slides, and I know Fabrizio will do this in more details, but the fundamental result follow from the fact that, let's just take the simplest example of the paradigmatic superoscillation. You have an exponential, e to the I ax. Well, this e to the ax is not only real analytic, but is extendable to a complex holomorphic functions. In fact, and that's the key property, which I don't think we thought about it for a while, this property is entire. So in other words, there is a function that is holomorphic everywhere, and whose restriction is e to the I ax. This allows us to use very powerful instruments to prove the permanence, if you want, of the evolution of superoscillation. What happens if you have functions that are real analytic, but they are not necessarily the restriction of a function that is holomorphic everywhere? Let me remind that the real analytic function, by its definition, is always the restriction of a function that is holomorphic in some neighborhood of the real axis, but not necessarily that is holomorphic in all of the complex plane. For example, if you take 1 over 1 plus x squared, that clearly is real analytic, is an extension. You can extend it to a holomorphic function, which is 1 over 1 plus z squared, but that's not entire, because when you get to I and minus I, you get stuck. There are not that many obvious differences in behavior of this function, but when we apply our theory, we try to study how you evolve, then you get into some interesting thing, because what we need to do is to study the dual of the spaces of this function. So this has led us to spend some more time in trying to understand the relationship between analyticity and more generally, not just superoscillation, but supershift. And again, I go back to supershift because in some cases, because supershift is another form of analyticity, because it's not the exponential anymore, but you have a family, you have a one-parameter family, if you want, of functions that is determined for large value of the parameter by just knowing the parameters in a small area. One of the questions is this relationship impacted in any way by where you choose the points? Now, I say this because the example I gave you so far may lead to think that you're just looking at the points y minus 2j over n. But in fact, in a work that we did with Yakir, and this was his idea, you can show that you can choose arbitrary points. So you can do what we call kind of irregular sampling. You don't need to start with the points irregularly spaced. So what happens if you have this more general kind of supershift or superoscillation in which the points here are spaced differently? And so we work on this, and what it turns out is that if you have a function that is the restriction of an entire function, so now you have a function holomorphic everywhere, like the exponential, that this implies a very strong form of supershift. In fact, stronger than the one that I described here. But the converse is not true. So the converse is not true. There are actually fairly good examples that show you the challenges. And then we study what happens when you have functions that are only holomorphic in some neighborhood of the real axis, like the case of 1 over 1 plus x squared. So that's a restriction of something holomorphic in a neighborhood, but not everywhere. What happens there? So the actual characterization of supershift within those functions is something we don't have yet, and it will be very interesting. So to be able to give a specific characterization will be a kind of a generalization of the notion of analyticity. And I think I will, I have some reference that I wanted to mention. The first one is the mathematical superoscillations that gave the state of the art, but now is old because it's 2017. So in fact, we are thinking about a revamping because since 17 to now, in 6 years, there has been so much progress. Many of the questions that were asked there are now being understood, and there are new questions. One of the things that we did there that is connected to the results of today was to study Dirichlet series, for example. You have Dirichlet series of exponential, and then apply superoscillation phenomena there to see what you could say. The second is this more recent, I dated it wrong when I was talking before. This is 2019. It seems like yesterday, but it's the roadmap on superoscillation. Again, state of the art, not just about the math. We wrote the section on the math, but there are many other things about applications and quantum significance. There is an interesting work of Barry and Klein in which he talks about the Talbot effect and connected with the Gauss sums there. And then this is the work that I described today. And I think I will stop here. Thank you.
All right, we have plenty of time for questions. Let's start with Andrew.
Daniele, what a treat. That's really exciting. Thank you very much.
Thank you.
A field, if you'll excuse the pun, in which you'd love to be Fourier limits is microscopy. And its inverse, which is even more important industrial, and that is some, extreme photolithography. Are there any ways that you can see that these superoscillations can be used to beat the Fourier limits in those situations, or is there a good reason why they cannot be used?
Well, I think that isn't that some of the work that I think Andrew and John have done? So the answer is yes. And that's one of the exciting applications of superoscillation. I don't know if you are going to talk about that. Okay, so he's going to talk about that in his talk today or this Friday.
I'm on the edge of, I can't wait till Friday.
Well, actually, what Andrew has shown is that you can beat in a different variety of situations. So you can actually use these ideas in different settings and not just the way we look at this here. So I think it's very applicable. Why most of what I described today is more of a theoretical nature. I think that they've been able to apply to radar imaging, for example.
Yes, so John will talk about radar in a few days, but I'll talk about optical superresolution in particular. Yeah.
And there are already experiments, actually, as Yakir was pointing out before, that shows how this can be applied. Because that's clearly one of the, you're able to generate this very high frequency light by using, low frequency. That's the key to beat the limit.
Marvelous.
It is.
Thank you.
Thanks.
Okay, next question. Yes, Toma.
Thanks for the talk, very interesting. I have a question about the Talbot effect. Can you go to the slide before the introduction of the Gaussian sum?
Can I go?
Can you go to the slide?
Oh.
It's before.
Which one? You stop me.
Maybe use it like now.
Here?
Yeah, can you hear me?
Yeah.
Great. Can you go to the slide before the introduction of the Gaussian sum?
This one?
No. Really in the beginning. In the introduction. Before that? Before? Yeah, that one. So this is really the introduction. This is the formula of the Talbot effect. And you show an application for quantum mechanics, but I just wonder one thing. When you have this formula, just on the mathematical level, and they see lambda is the wavelength, and they it's the period, and they are the same units, so this unitless, the denominator, just observed that you have this thing, and if you divide lambda by delta t and a by delta t, you have something that you can say that it is mathematically the same as the inverse of Lorentz factor in special relativity. And essentially, this formula gives you geometric sum of the inverse of Lorentz factor. And I just wondered if there is some relations known relation with special relativity for this? Because I know that the background of this is non-relativistic.
If there is, I'm not aware. I see what you're saying, and I've never seen it before, but that doesn't mean that it's not there.
Great.
So you're thinking about special relativity and using the same instruments to try to understand.
Yeah,
that,
it's similar because here
But-
lambda it's less than A, right? And
Right.
and
But this is only, I mean, this only talks about the distance between one image and its replication.
yeah, but if you divide lambda and A,
Right, no, I get that, but how would you apply these ideas to
I
that?
don't know.
Okay,
Maybe there is something, I don't know.
thank you.
Okay, other questions?
Maybe it's sort of, I don't know if
Use
it's
your,
relevant.
use your microphone.
You say that you can very often, I mean, even from an infinite dense set of points, analytically continue the function. And certainly if you have an infinite series and it converges within the unit circle, it's a basis for continuation.
Right,
But there is this kind of Hadamard gap theory
right,
that says that if you keep skipping and skipping, you will never be able to continue.
right.
So does it have any implication for you in a negative way?
So this is a very interesting question. I think we talked about this the very famous night that we started studying about this. Yeah, yeah. So there are theorems like the Fabry gap theorem, the Hadamard theorem. But their nature is somewhat, I thought about that because I remember your comments. The nature of those theorems, though, is different from here. It tells you that there is a natural boundary for the analyticity. In other words, if you have a series that have enough gaps, enough jumps, so enough zeros in the coefficients, then you can't move beyond. And I don't think that, even though it's reminiscent of this, I don't think it really applies because here you have the values in infinitely many number of points in the vicinity. So I think there is some kind of resonance, but I really don't think there is a connection. And I thought about that because I remember when you posed that point.